So I've prepared a couple of solutions to limiting reagent problems. Let's look at this first one. The question is disulfur dichloride, S2Cl2, let's see if my pen will work here, is used to vulcanize rubber, and it can be made by treating molten sulfur with gaseous chlorine. So here's our balanced chemical reaction. S8 liquid plus 4Cl2 gas goes to 4S2Cl2 liquid. And what we're told here is that we're starting with a mixture of 32 grams of sulfur and 71 grams of Cl2. Just the fact that we're given masses of two different reactants is one tip-off that it's a limiting reagent problem, and that we've got to think about, got two amounts here, which one is going to get used up first? So my question is asking, first, what is the limiting reagent? Second, what's the theoretical yield of the product? And then third, what mass of the excess reactant remains when the reaction is completed? One of the things that I like to do when I have a stoichiometry problem like this is to just get the molar masses out of the way. And I'm going to assume that you know how to do that. So I'm just going to write them up here. Let me just make that better. S8, its molar mass is 256, this pen is awful, 0.48. Cl2, its mass is 70.90, and this is grams per mole. Grams per mole. And S2Cl2, its molar mass is 135.02 grams per mole. So I'm assuming you know how to do that kind of problem, or to determine what the molar masses are, by just adding up the masses of all of the component atoms. All right, so now that I have those molar masses, because I think they're going to be useful to me, I'm going to ask, what is the limiting reagent? In order to determine the limiting reagent, I need to know how many moles of each reactant I have, because I can't look at the masses themselves, I have to look at the moles. So my second step is going to be to take my masses, 32.0 grams of sulfur, and convert that to moles. So I know that in 1 mole there are 256.48 grams, and that's going to give me 0.124766 moles of S8. And I'm also going to determine how many moles of my other reactant, 71.0 grams of chlorine gas. And I know that in 1 mole there are 70.90 grams. So I get 1.0014 moles of Cl2. All right, so that's how many moles of each thing I start with. And I can see right away that I have more moles of Cl2 than I have of S8. But I can also see that in my balanced chemical equation, I need more Cl2 than I need of S8. So now I have to figure out, what am I going to run out of first? So I'm going to ask this question. If I were to react all the S8, how much Cl2 is needed? And the way I'm going to do that is I'm going to start with my moles of S8, which is 0.124766 moles of S8. And I'm going to use my stoichiometry from the reaction to figure out how much Cl2 would react with that. And so what I know is that for every 1 mole of S8, I need 4 moles of Cl2. And that gives me 0.49906 moles Cl2 needed, meaning that's what's needed to react all the S8. So since I have more moles of Cl2 than this, right, because I have more than essentially half a mole of Cl2, that means I'm not going to run out of Cl2. Will not run out of Cl2. That means I will run out of S8. So therefore, S8 is my limiting reagent. Okay, so that's the first question. What is my limiting reagent? Done. The second question is, what is the theoretical yield of S2Cl2? The theoretical yield, or the mass of the product that I think I can get, is going to always be determined by the limiting reagent. So I'm going to start with my moles of S8, point 1,2,4,7,6,6 moles of S8. And now I'm going to go from S8 all the way to the product. So I'm going to, I'm going to look at the relationship up here between S8 and the product. So I know that for every 1 mole of S8, I'm going to get 4 moles of S2Cl2. Now in this case, I'm looking for the theoretical yield of the product. So if I did my calculation right now, I would get moles of S2Cl2. But theoretical yield is generally a mass, and so I'm going to go ahead and add another conversion factor in here to convert my moles of S2Cl2 to grams. And again, I'm going to use the molar mass that I figured out earlier, and that's going to be 135.02 grams per mole. And that gives me 67.3836, or 67.4 grams of S2Cl2. That's my theoretical yield. Okay. So my last question was, what mass of the excess reactant remains when the reaction is completed? So what we know is we started with, well, first of all, our excess reactant is going to be Cl2, right, because it's not the limiting reagent. So, whoops, that's what I want. So this is the reactant we're thinking about. This is what we started with. We started with 1.0014 moles of Cl2, and we used up essentially half a mole. Used up. And so what we want is what's left. Cl2 left is going to be 0.50234 moles of Cl2. This is an interesting sig fig problem because it's addition and subtraction, and so I'm going to be limited to the fact that I have to be, the only digit I know there is out to the hundredths place, so I can only know out to the hundredths place here. Okay, so what I did was I took 1.0014 minus 0.49906, and then this is what I got. So that's how many moles of Cl2 are remaining. I want to know what mass is remaining, right up here. That's what I'm after, is the mass. And so I'm now going to convert this number of moles to grams. That's 70.90 grams per mole. And what I get is 35.61 grams, but I'm limited to 2 sig figs, so I'm going to get 36 grams of Cl2 remaining at the end. Okay, so let's do another limiting reagent problem. In this case, aspirin, which has this long, complicated formula, is produced by the reaction of salicylic acid, which is this reactant here, and acetic anhydride, which is this reactant here. And so our situation is if we mix 100 grams of each of the reactants, salicylic acid and acetic anhydride, what is the maximum mass of aspirin that can be obtained? That's the same thing as asking what's the theoretical yield of aspirin. Once we figured that out, then we want to know how many more grams of the limiting reagent would you need so that both reactants could be consumed by the reaction. But let's focus on A first. So again, we're given masses of 2 reactants, so that tells us it's a limiting reagent problem. And one of the first things I'm going to suggest we do in this case is because we've got a reaction that has some pretty complicated organic formulas in it, and they're complicated for a reason. They tell us something, but for the purposes of Chem 111, we don't actually need this level of complication. So the first thing I'm going to do is I'm going to rewrite the reactants and the products so that they're a little more simple for us to understand. So if I count up all the carbons, in this case, hydrogens and oxygens, I get C7, H6O3. So that is salicylic acid, has that formula. The acetic anhydride is C4H6O3. And the aspirin is C9H8O4. Now we don't actually need the last product. We don't even know what the name of the last product is, but I'm going to write its simplified formula down anyway and just say one thing about it, H4O2, C2H4O2. When I did this, I made sure that the reaction was still balanced so that to make sure I hadn't made any mistakes. So this is what we're working with. Okay. As was the case in the last situation, the last example, I'm going to write down the molar masses so that, because I'm pretty sure I'm going to need them. So I'm going to write salicylic acid, which is my first reactant, and it has a mass of 138.13 grams per mole. The acetic anhydride, and I'm just going to abbreviate it right there, has a mass of 102.10 grams per mole. That's a 0. And aspirin has a mass of 180.17 grams per mole. Okay, so I'm just going to kind of put those things off to the side there because I'm going to need them later. All right, so now I can go back to my main question, which is if I mix 100 grams of each of the reactants, what is the maximum mass of aspirin that I can obtain? So in order to really figure this out, I need to convert my masses to moles. So let's figure out what the moles of each of my 2 reactants is. So if I start with 100 grams of C7H6O3, which is my salicylic acid, and I convert that to moles, because I know that in 1 mole there are 138.13 grams, so that gives me 0.723955 moles, and there are 4 sig figs there. So that's how many moles of my salicylic acid I have. Likewise, I can do the same thing for my acetic anhydride, which is C4H6O3. If I convert it from mass to moles, I'm going to use 102.10 grams. And what I get in this case is 0.979431 moles. Now in this case, notice that I have a stoichiometric relationship here between the two reactants that's 1 to 1. So I know that to react all of them, I'm going to have the same number of moles of each one. And since I have fewer moles of salicylic acid, that means I'm going to run out of salicylic acid first. So this is my limiting reagent. Will run out first. Okay, so I know what the limiting reagent is, but that's not really what the question asked me for. The question asked what's the maximum mass of aspirin that can be obtained. Now I needed to figure out what the limiting reagent was because that's what's going to determine how much of the product I can make. So once we know what the limiting reagent is, we always use that to determine what mass we can get of the product. So I'm going to use the moles of my limiting reagent, 0.723955 moles of C7H6O3. And I'm now going to relate it to, I'm going to relate the moles of my limiting reagent to the moles of aspirin, because that's what I'm after, is the theoretical yield of the aspirin. So I know that this is also a 1-to-1 ratio, 1 mole of C9H8O4, which is aspirin, to 1 mole of C7H6O3. Now, I'm going to go ahead and convert what is now, if I were to do this calculation, because the moles of salicylic acid cancel, I'm left with moles of aspirin, but I want mass of aspirin, so I'm going to just go ahead and do that. 180.17, I'm using the molar mass. And what I get is, let's move this up. What I get is 100, oops, let me go back to my pen, 130.4 grams of aspirin. That's my theoretical yield, or what's the maximum mass of aspirin that could be obtained. Okay? Now, that's part A. Part B is how many more grams of the limiting reagent would we need if we wanted to react all of both reactants. So in this case, what we've got is we know that we had 0.979 moles of the acetic anhydride, and we want to know how much more salicylic acid would we need so we could react everything. So in this case, what we're going to do, let me make myself some space here, is we're going to say we need 0.979431 minus 0.723955 moles, which is equal to 0.255476 moles of C7H6O3 needed to react all of the acetic anhydride. Okay, so if we had this additional amount, then we would have 0.979431 grams of both things, and we could react it, and everything would react. The question, however, asks for how many more grams of the limiting reagent do we need. So let's go ahead and take this and convert it to mass. 0.255476, whoops, not grams, moles of C7H6O3. Remember, that's the salicylic acid, and that's how many more moles of salicylic acid we need. And now we're just going to convert that to mass. 138.13 grams per mole, and that gives us 35.2888, or 35.29 grams of salicylic acid. And remember that what that means is that's how many more grams of the limiting reagent, how many more grams of salicylic acid we would need so that both reactants could be consumed. So what that tells us, interestingly, is that, let me get my pointer here. How do I think it's this. If we had 100 grams of the acetic anhydride, we would need 100 grams of the salicylic acid plus another 35 grams in order to have the right number of moles to react in our 1-to-1 ratio. Okay, let's do one more limiting reagent problem. In this case, we have a deep blue compound, which is copper with 4 ammonias on it and a sulfate. Don't worry about how to name it. So it's made by this reaction here. Copper sulfate plus 4 ammonias goes to our product. And the question is, if we use 10 grams of copper sulfate and excess ammonia, what's the theoretical yield of the product? So in this case, this is actually telling us what the limiting reagent is. When we're given the mass of one reactant and told we have excess of the other, by default that means that the copper sulfate is going to be the limiting reagent. And now we know to use that to determine the theoretical yield of the product. So let's start, because we always start with our limiting reagent then, we're going to start with our 10 grams of copper sulfate. Oh, one thing I should have done is written down my molar masses. So let's go and do that. Copper sulfate has a mass of 159.61 grams per mole. Ammonia, in case we need it, has a mass of 17.04 grams per mole. And our product, copper NH3,4SO4, has a mass of 227.77 grams per mole. Okay. All right, so I'm going to move this so I have more space. Okay, so let's go back. We have already determined that the copper sulfate is by default our limiting reagent because we've got an excess amount of ammonia. And so what we want to figure out is how much of the product can we make. So we always start with our limiting reagent, in this case copper sulfate. Our reaction tells us that there's a relationship between the amount of copper sulfate and the product that happens to be 1-to-1. But it's 1-to-1 in terms of moles, so we've got to convert to moles no matter what. So what we're going to do is convert our copper sulfate to moles. In every 1 mole there is 159.61 grams. And we know from the balanced chemical equation that there's, for every 1 mole of the product that we're going to get, CuNH3,4SO4, we will have reacted 1 mole of copper sulfate. And we can now, I'm going to add to my list here. That will allow us to cancel moles of copper sulfate. Grams of copper sulfate will have canceled. So that leaves us with moles of our product, and we want the theoretical yield, which is in grams. So now we just need to convert our moles of product to mass of product by multiplying by its molar mass. 227.77 grams per mole, and that gives us 14.270 grams, or 14.3 grams of product. Now the second part of our question says, if you isolate 12.6 grams of the product, what is the percent yield? So what that tells us is that even though we predicted that we could get 14.3 grams if everything reacted, in a lot of cases the atoms, when they interact with one another and react, not everything gets converted into products. So in this particular case, we got less than what we expected. So the percent yield, percent yield is equal to the part, in this case the part that we got, over the whole, which is what we predicted, times 100. So in that case we're just going to say it's 12.6 grams over 14.3 grams times 100. And that gives us 88.2945%, or 88.3% yield.